Hello friends. So in this lecture we will look at the aerosol properties of the indoor sources themselves. So the first source we will look at is cooking. Cooking is generally the most dominant source of indoor aerosols. We often cook several times a day, and we use different types of fuels. We use different types of ingredients and different types of oils. So there are a different wide variety of aerosols, and also just because we do it so many times, it is the number of aerosols, the quantity is also very high due to cooking. Therefore, cooking is the most important dominant source of indoor aerosols in terms of both the mass particle number of aerosols and the mass of the aerosols. And as I said, this is because of the very high emission rates when looked at, for example, per day. The level of indoor particles during cooking events will increase by orders of magnitude compared with non-cooking periods. So orders of magnitude meaning the levels of indoor particles can raise by 10 times or 100 times compared to the time when there was no cooking happening. The particles by number emitted from cooking activities are mainly distributed in the ultra fine range, basically ultra fine range, and up to 80% with diameters less than 0.1 micrometers. So cooking basically emits predominantly in the ultra fine range. The measured particles generally have been seen to be in the range 0.006 to 20, but the particle number mode, meaning the maximum amount, the maximum number of the count of the particle size, was from 0.03 to 0.06 meter. That means most of the number of particles would be somewhere in like 0.03 or 0.04, 0.05, 0.06. These were the size range where there was the most number of particles. In terms of mass, the most of the mass was occupied by particles in the range 0.1 to 0.4 micrometer. And of course, the particle number mode or particle mass and their peaks and distributions depended largely on cooking temperature, the heating source, and the type of cooking oil and food that was being employed by the people. The particle number size distribution. So particle number size distribution means the number of particles per unit volume for any size. So how many particles in 0.1 micrometer, how many particles in 1 micrometer, and this is how we will get our particle number size distributions. And it can be affected by the type of cooking oil as well. For example, is it a corn oil, coconut oil, olive oil, or peanut oil? It was found that for the same oil temperature of about 197 or around 200 Celsius, the particle number size distribution were showing a wide range, but the mode for cooking with peanut oil was at 0.025 micrometers. So the maximum number of particles were in the 0.025 micrometer size. But when we looked at soybean, when the soybean oil was at the same temperature and the cooking was done, most of the particles, or the particle mode, which means the maximum number of particles, were in the 0.08 micrometer range. Then in another study it was observed that when we looked at the evolution of particle size distributions during toasting, grilling and oven baking, there was an occurrence of nanoparticles less than 10 nanometer or less than 0.01 micrometer, which was sort of emitted as an initial burst. Like as soon as the activity started, there was an increase in the immediate burst, like immediate increase in the size, in the number of particles in this size. The emission strength during this initial step was stronger in the presence of small liquid film of semi-volatile organic compounds on the heater surface. So we have this toasting, grilling and heating, which are like heating surfaces, and if there was a layer of some volatiles, as soon as the heating started, these volatiles will be suddenly released. So the volatile fraction will suddenly vaporize, and then they will rapidly form new particles via oxidation or while condensing on existing particles. So they will immediately form new secondary organic aerosols, or they will condense into existing particles. So there was like an immediate initial burst in the number of such particles. In general, when people have looked at deep frying with oils and grilling, and and then when they have grilled sausages, particles in the diameter of 0.05 to 0.35 micrometers have been emitted, and generally these have been of hydrophobic nature. This is because these particles were consisting of non-hygroscopic, so these particles were not going to absorb much moisture, and this is because the compounds were non-hygroscopic, and these were like hydrocarbons and black carbons. In one study, the chemical components of PM 2.5 were measured, and this PM 2.5 was emitted from the 4 gas cooking methods such as pan frying, stir frying, boiling and steaming. It was found that the fine particles were emitted, and they were mostly organic carbon 50 to 75%, elemental carbon, which is often denoted as EC, 7 to 12%, then inorganic species 4 to 20%, and metals, which were about 2 to 4%. The aerosols emitted from oil-based cooking methods consist generally more of organic components such as organic carbon, PAHs and organic sort of ions and metals, and this is natural because organic compounds are the major component of cooking generated aerosols. Aerosols that were produced from more water-based cooking methods contained more water-soluble ions. So this is of course natural. Then in the next source we are going to look at wood burning, and this is done in stoves and fireplaces. And it has been found that when the particles are released from the domestic wood burning, the particles are predominantly in the fine, which is less than 1 micrometer size range. However, many different particle number size distributions have been reported, which means it is not clear cut that the number size distribution will remain the same, although this particle sizes will generally be less than 1 micrometer, but the distribution will be very variable, and both unimodal and bimodal particle number size distributions have been observed. So that means when we are looking at unimode, there is particle distribution and then single peak, but when we have bimode, there will be 2 places where we will have more peak. So there may be 2 particle sizes where we will have high number concentrations. It has also been seen that when aerosols are emitted during the flaming phase, there was a unimodal number size distribution with a peak around 0.04 to 0.06 micrometer. So we have this flaming phase, but when we have this smoldering phase, the aerosol showed a bimodal distribution. So there are two peaks, one at 0.07 micrometer, which was a major peak, and then another smaller peak at 0.25 micrometer. So there were two places where the number counts were higher. Now the particle number size distributions can also change during the burning process. Generally there is a bimodal size distribution with a nucleation peak mode of around 10 to 20 nanometers, so about 0.01 to 0.02 micrometer, and one Aitken peak mode at 40 to 50 nanometers. So this is 0.05 to 0.04 nanometers. So there was a bimodal size distribution with one peak in nucleation mode, one peak in Aitken mode in the first 10 minutes of burning. But when we wait for a longer time, the two peaks then transform to a single peak. So the bimodal distribution transformed to a unimodal distribution with a peak at around 63 nanometers, so a bit higher than this. So this is 0.06 micrometers. So instead of two peaks, after some time only one peak was observed, and this could be because we could have particles in the nucleation mode that can be formed from the gas phase conversions of precursors during dilution and the cooling of the exhaust gas. It has also been reported that the particle number size distributions from wood burning could be affected by many factors, such as one could be the type and design of stove and fireplaces. So that will affect how the wood is burned and the extent of wood is burned. The type of wood itself, for example, one can be using hardwood or softwood. The properties of the wood itself, for example, moisture content, and if the wood is a log versus a branch. The phase of combustion we are looking at, ignition, flaming or smoldering. For example, we just saw where flaming had one distribution and then smoldering had unimodal flaming. Flaming had unimodal distribution and smoldering had a bimodal distribution. Also, it will depend on the particle number size distribution will depend on the combustion process and the experimental conditions or the prevailing conditions, such as the temperature, the measurement point, the dilution ratio and the combustion air supply. In one study, the particle number size distribution was compared between the emissions from a residential wood stove and the emissions from a fireplace. So researchers measured the particle number size distribution when a residential wood stove was used versus when there was a fireplace existing in the setting. So from the PNSD obtained from the fireplace emissions, there was a single accumulation mode around 70 nanometer or 0.07 micrometer. The PNSD, particle number size distribution from stove test, exhibited two modes, one at 15 nanometer, that is 0.05 micrometer, and the other mode at 40 nanometer, which was 0.04 micrometers. So fireplace single mode, stove two modes. Then when particle emissions were studied from rice straw burning, there was a unimodal distribution with the accumulation peak mode around 0.1 to 0.2 micron or 100 to 200 nanometer. But when the particle emissions from burning of oak and fine wood were analyzed, there was a bimodal distribution with a major peak around 100 nanometer, that is 0.1 micrometer from flaming combustion, and at 600 nanometer, which is 0.6 micrometer from smoldering combustion. So the type of wood as well as the combustion type is influencing the particle number size distributions. The particles that are emitted from the combustion of wet biomass could be spherical, could be agglomerates of spherical particles, and could be crystalline agglomerates. Tar balls, for example, they are likely formed by gas to particle conversion within the smoke plumes, and they would be in both small and large clusters with diameters between 30 and 600 nanometer, that is 0.03 micrometer to 0.6 micrometers. However, less abundant particles were found as the crystalline agglomerates. Now we were looking at particle number size distributions. Now even the shape of the particle will depend on the type of biomass fuel and the type of stove. For example, the combustion of dry biomass has been shown to release spherical particles which were associated with the smoldering phase. However, fractal aggregates, which consisted of primary particles with diameters around 30 to 50 nanometer, that is 0.03 micrometer to 0.05 micrometer, and they occurred mostly in the flaming phase. So again, phase is influencing not only the size distribution but also the shape of the particles. Generally, when we are saying biomass burning, organic matter is the most dominant fraction of particles in biomass burning. It has been found that organic carbon constitutes almost 50% of PM2.5 in the emissions from burning of 7 wood species and briquettes in both the fireplace and wood stove scenario. So, regardless of the wood type and the stove type, it was found that organic carbon contained almost 50% of the PM2.5 fraction. It has been found that water soluble ions are also major component of biomass burning generated particles. So when biomass is burned, the particles have more water soluble ions, and this generally range from 0.64%, which is not very high, to 13.5%, which is a decent fraction, depending strongly on the wood type that was being burned. It has been found that the most abundant organic compounds that are contained in particles from wood burning emissions are sugars such as levoglucosan, monomethyl linositol, galactosan and manosan, then methoxyphenols, then organic acids which could be methoxy, resin, aromatic dicarboxylic, alkanoic, substituted benzoic, alkenoic and alkanoic acids. So various compounds can be found when wood burning is taking place. So we find that aerosols that are generated from the burning of different types of woods and different types of conditions lead to a large variation of the hygroscopic growth factors also. How hygroscopic those aerosols are. They can range from extremely hydrophobic particles, which is basically pure elemental carbon, to hydrophobic, to less hydrophobic, to hydrophilic, so water loving hydrophilic carbonaceous particles and very hygroscopic particles. So a wide variety of particles are possible. In the submicron size range, smaller particles were likely found to be more hygroscopic than the larger particles. There were more soot particles in large particles, which is diameter less than 100 nanometer or 0.1 micrometer, which could lead to low hygroscopy. And the hygroscopicity of particles during the smoldering phase decreased by aging. So the more we waited, the less hygroscopic the particles became. Now we will change to another type of burning, which is incense burning. Incense burning generally produces particles in the fine size range. In this case, the fine size range means less than 0.25 micrometer diameter. Generally, particles by number, they will be in the accumulation mode with the count mean diameter about 80 to 190 nanometer, which is 0.08 to 0.19 micrometer. The particle number size distributions of emitted incense particles depend strongly on the ingredients of the incense itself. So again, it can be very variable. In one study, the sizes of particles was analyzed from the burning of 4 types of incense sticks. For example, Chinese smokeless sandalwood, Japanese aloes wood, Indian sandalwood, Taiwanese sandalwood. And for all these, different count median diameters of the particle number size distribution were observed and ranged from 93 to 143 nanometers, depending on which stick was analyzed. The count median diameter of the particle number size distributions observed for incense smoke aerosols were found to be typically larger than those emitted from other combustion sources such as cooking, wood burning and diesel combustion. Particles emitted for burning of incense could grow rapidly as a result of condensation and coagulation, especially or during the slow combustion at the room temperature. So when these particles are there, they will condense and coagulate. There is a small peak around 30 nanometer observed immediately after the lighting of incense. This is possibly due to the formation of nanoparticles through oxidation of semi-volatile organic compounds, which are emitted from the incense smoke during the first 10 minutes of burning. Incense smoke aerosols are generally found to be dominated by non-coalescing and weakly bound aggregates, and these aggregates are also of irregular shapes, which could be plate or block-like shapes, and these could be a result of production due to unburnt burning of incense organic materials such as the powdered charcoal and inorganic filler minerals such as the finer powdered limestone. The morphology of particles that are produced by incense burning also depends on the type of incense sting used. In general, both liquid and solid particles have been detected. In terms of hygroscopic properties, particles can be found as nearly hydrophobic for ultrafine and less hygroscopic for accumulation mode. So hydrophobic for ultrafine and less hygroscopic. So little bit hygroscopic basically for the accumulation mode particles. When this PM 2.5 in incense smoke is analyzed by mass, the carbonaceous particles, especially organic carbon, which contain organic carbon more than 90%, such carbonaceous particles all contributed to 66 to 74% of this mass fraction. Whereas the ionic species such as Na plus, K plus, Cl minus, NO3 minus, this 3 subscript, and NO3 minus, SO4 2 minus, PO4 3 minus, they are about 2 to 11%. Metals around 0.3 to 3.3%. And by some within these metals, iron and aluminium have been detected to be the main metals. So incense burning is a very interesting phenomena, in that the reactive oxygen species were also found to be produced or formed during the incense burning. Then with respect to organic composition, anhydrous sugars were found to be a major component of the incense smoke particles, and they contributed, or they were comprising of around 47 to 52%, so almost half. Followed by carboxylic acids around 12 to 17%, and then followed by the sugar and alcohols 4.4 to 5.4%. The higher metal content in the incense sticks, for example sodium and potassium, this can enhance the smoldering combustion and also influence the rate of burning and the amount of ash and particles that are emitted per amount of incense burned. So that is the ash and particle emission factors, how much the ash and particles are emitted due to the process of the incense burning. Now we will move to tobacco smoke. So as we have seen so many times, tobacco smoking is well known as a major source of indoor aerosols. The particles that are emitted from cigarette smoking typically show a unimodal particle number size distribution with a peak mode around 100 to 200 nanometer, which is 0.1 to 0.2 micrometer. So the peak is in generally one place, unimode, and that place is around 0.1 to 0.2 micrometer, and this peak generally depends on the experimental conditions itself. For example, the chamber or room volume and the ventilation being employed. Then the smoking conditions, which could mean the number of cigarettes being smoked, the smoking time and smoking cycles, and if the person is making puff, and that itself influences the particle size distribution and the mode, location of the mode. Then it also depends on the type of smoke, which is mainstream versus side stream smoke, the type of cigarette, which is conventional cigarette versus e-cigarette, electronic cigarette, and also the chemical composition of the cigarette, which means what went into the making of the cigarette itself. Then the aerodynamic processes, the aerosol dynamic processes that influence the evolution of particle number size distributions of cigarette smoke are coagulation, and then evaporation of semi-volatiles, and water condensation. It has been found that the count medium diameter for exhaled mainstream smoke, which is 250 nanometer, is more than the inhaled mainstream smoke, which is around 190 nanometer. And this indicates that the smoke aerosols sort of grew. So we inhaled some aerosol, it grew, so some deposited, and the grown aerosol is now exhaled. So the median diameter for the exhaled smoke is more, the count medium diameter is higher than the inhaled. So we inhaled, it grew inside, and then we exhaled that grown aerosol. The hygroscopic properties of cigarette smoke aerosols also showed a significant growth for aerosols greater than 200 nanometer under highly humid conditions. So naturally high humid conditions signify help in the growth of hygroscopic aerosols. Now there are three exposure pathways actually for tobacco smoke by inhalation. One is active smoking, which is the inhalation of the mainstream smoke from the burning of a cigarette directly into the smoker's respiratory system. The second pathway is second-hand smoke, or the environmental tobacco smoke, which is basically a mixture of side stream smoke emitted from the cigarette smoldering and the mainstream smoke which is exhaled by the smoker. The third pathway is the third hand smoke, which consists of the chemical residues of tobacco smoke pollutants, and these residues cling to room and clothing surfaces long after smoking, and then these can be re-emitted to the indoor air, and when the person inhales this air, the person is basically having a third hand smoke. So these chemical residues from tobacco smokes will be on the room and clothing surfaces, and then when they are re-emitted, another person inhales them, and that becomes a third hand smoke. And we have seen before already that the tobacco smoke has a lot of different constituents, which could be alkanoic acids, alkanes, N-heterocyclics, and these have been found as the most abundant compounds present in conventional cigarette smoke aerosols. E-cigarette aerosols can also consist of glycerine and propylene glycol, then water, some flavor and nicotine. And these aerosols also contain or generally may contain a minor fraction of carcinogenic and toxic compounds such as tobacco specific nitrosamines, PAHs and trace methyls, and these are all have been found in aerosols emitted from the tobacco smoking. After tobacco smoking, we will move to cleaning, and then it has been found that these cleaning activities generate particles, and these generated particles are in a very wide size range, ranging from several nanometers to micrometers in diameter. So very wide range. Now indoor aerosols can be generated from three types of cleaning activities. One is vacuum cleaning, then the other is wet cleaning with chemicals, and the third sort of when we are using a air freshener. It's also sometimes we can term it or club it with cleaning. So vacuum cleaning, wet cleaning with chemicals, and use of air fresheners. Vacuum cleaning, so the motors that are in vacuum cleaners, they are a source of ultrafine particles. In a study, the particle number size distribution was observed across 21 vacuum cleaners, and it showed a unimodal distribution with a wide range of count median diameters. So although the distribution was unimodal, the count median diameters were 14 to 146 nanometers, generally mostly being less than 30 nanometers. This particle number size distributions were attributed to many factors such as the effect of temperature, the type and the presence of dust chamber or dust bag, the motors, and even the type of the high efficiency particulate HEPA filters. Then VOCs that are emitted from the heating of vacuum body materials and the grease and oil that is used in the machinery for lubrication, for example, these could also contribute to ultrafine particle formation. Now this vacuum cleaning also produces a huge amount of larger particles such as coarse particles, and sometimes also bacteria can be suspended due to bioaerosols, and so vacuum cleaning can also produce or help in the emission of these particles. Particles that are of diameter more than 10 nanometers are consisted primarily of chemical binders, metals such as copper, then elemental carbon and organic carbon during vacuum cleaning. These chemical compounds have been attributed to the mechanical abrasion within the vacuum cleaner, such as rubbing and arcing between copper commutator and the carbon rods. Sometimes the ultrafine particles have been found to consist almost entirely of copper, which means some sort of release of the machinery components due to abrasion. Then we have wet cleaning and air fresheners. So cleaning with chemicals on the use of air fresheners is a major source of submicron particles. This can be generally due to the formation of secondary organic aerosols by the oxidation of chemicals emitted from cleaning products. So cleaning products will emit some volatiles and they will get oxidized and form secondary organic aerosols. During the cleaning activities, a dominant fraction of ultrafine particles has been generated. So that is the observation, that during such cleaning activities, ultrafine particles are generated. And the PNSDs has shown a unimodal, so single peak distribution with the peak happening at a diameter of 31 nanometer or 0.031 micrometer. Again, these ultrafine particles have been attributed to secondary organic aerosols resulting from the reaction between ozone and limonene emitted from the cleaners. In another study, it was indicated that ozone and limonene in indoor air are a major source of indoor submicron particles. So similar conclusions as just now before. Even at low concentrations of ozone and limonene, reaction between them can still occur to form secondary organic aerosols. So it's quite likely that secondary organic aerosols can be formed. Cleaning products and air fresheners are generally a main source of secondary organic aerosol precursors, especially terpenes, for example limonene, A-pinene and bipinene, which can then react with ozone and yield the secondary organic aerosols. In general, for example, ozone terpene reactions will produce hydroxyl radicals, which are oxidizing agents, and they will react rapidly with the organic compounds and cause indoor SOA, indoor secondary organic aerosol formation. So organic compounds will comprise majority of such particles. The effective density is around 0.9 gram per centimeter cube. And then we have some major chemical components of cleaning generating aerosols such as levulinic acid, succinic acid, 2-methyl butanoic acid, pentanedioic acid, ketolimonene, dimethyl glyoxal and 4-hexopentanol. So we can now summarize this lecture and the whole week, in which we have seen some basic properties of aerosols, primarily in terms of the sizes and the different modes, nucleation mode, Aitken mode, accumulation mode, coarse size mode. Then the pathways of aerosol removals within an indoor environment, which could be deposition, condensation, evaporation and other processes such as coagulation that may happen. And then in this series we have also seen the properties of aerosols by indoor sources.